So if we're looking at the cardiorespiratory system, we are going to be talking about two systems here. We're going to be talking about, and again, it's kind of an interdependent system thing, right? So this is going to be our cardiovascular system. That's the heart, the lungs, the blood vessels, and the respiratory system, which is like the lungs and all the tubing attached to the lungs. So purpose of today's lesson, really quick. Hey, Daryl, I'm just going to have you hit the mute button real quick, just because the papers and stuff.
More feedback.
Yeah, you're good. If you got a question, though, please chime in. So we want to give you guys an understanding of how that system is going to work. We want to understand the structure and the function of, and I love the way they got this, but it's like the cardiovascular system, the respiratory system, and the cardiorespiratory system, which is like putting them together. How they relate to human movement, a couple oxygen testing procedures that are out there. So, some of our fitness assessments and stuff. And then we'll look at how like oxygen is related to, the way that we produce all of our energy. So when we're talking about the cardiorespiratory system, like I said, this is both of those systems coming together. When you think about like your lungs job is to extract oxygen from the environment. And then the cardiovascular system's job is to pump that oxygen around. So these systems obviously do work very, very intimately together in order to provide your entire body with oxygen, because there is nothing more vital on this planet in terms of like keeping us alive than oxygen, So we definitely need to be able to pump it around. Otherwise, our cells can't output any energy. So as we're talking about it, if we're talking about the cardiovascular system, like I said, it is going to be our heart, yes, but it is also all of the blood vessels running throughout our body. You can see those in different places here, right? Traveling around, supplying all the various tissues that we've got with blood, but it is also all of the blood itself. So we need to understand that like when we train, we are not just making our heart stronger, although we absolutely are. It's made of muscle, actually, which is why, we talked about muscle anatomy yesterday. Well, your heart is made out of cardiac muscle. You guys might remember, yesterday we talked about the difference between type 1 muscle fibers, which are like endurance type fibers. And we talked about type 2 muscle fibers, which are like strength and power type fibers. Cardiac fiber would be like type 1/2. Like it's the super endurance fibers, you know what I mean? Like if type 1 is endurance, because it has more mitochondria and lots of blood flow, well, your heart is absolutely crammed full of mitochondria. It is able to output energy. Think about like the duration of these exercises, right? Like I always like to break down the difference between type 1 and type 2. I can actually probably find this type 1. I'm sure somebody else has already made an infographic about this. I mean, that's close, but I was actually looking for repetition ranges. But this picture will kind of work. You think about like your type 2A versus type 2B. Type 2B is like full on short duration sprints. Think about like 100-meter dash, or if you think of it in terms of like repetition ranges, I would say anywhere from like 1 to 5 repetitions, right? And then you've got like your type 2A, which is like fast twitch, but like, somewhat oxidative. So that's going to be like type 2A. In terms of a runner, that'd be like a 400-meter dash or like an 800-meter dash sprinter, like anybody in here do track? Did anybody do track and field? Like if you did track, yeah, you'll know that like the 400 is arguably one of the hardest events in sports because it's
which I won. Sorry.
Love that. Because the thing is, it's just short enough to sprint the whole thing, but it's just long enough to make you throw up. You know what I mean? like it is still very much a sprint the whole time, but it's exhausting because it's just one super, super hard lap. So what ends up happening is like you're getting to just the very end of the fast twitch fibers there. And there's 800 meters as well, which like as a high schooler is also very, very difficult, but it's just long enough to where you start tapping into like endurance type fibers. Although on like a pro level, the 800 meter dash eventually becomes like full 2A muscle fibers. And then you got your type 1 muscle fibers, which is like long distance, right? Anything that's going to be greater than 2 minutes in duration, basically, is going to utilize type 1 muscle fibers. So now think about your freaking heart. I mean, it's been working since before you were even, before you entered this world, like your heart's been working nonstop since before you were born. I would say that's pretty good endurance, it's been running nonstop 24 hours a day, 365 days a year. That to me is as endurance-y as it gets, So that's really what we mean. When I say like your cardiac muscle is muscle, but it's like super endurance muscle, we are going to see a lot of long, intense duration, long, low intense duration exercise here. So that's the heart itself. It's this muscular blood pumping organ that really does kind of continue working throughout like your entire life. So we do like to say that it is a muscular pump, right? When you think about like what a pump is, it's something that generates pressure, right? Like a bicycle pump, like brings air in as you draw it up. And then like, as you press down, that air gets trapped because it can't backflow. So it has to go into the tire. So it's pumping air from like the environment into the tire of your bicycle, or, like an air pump in like a fish tank or something, pulls air out of the environment and pumps it into the tank, right? And that's what pumps do, right? They move air from one place or another, or they move water from one place to another. So in this case, this is a muscular pump that's designed to push blood throughout the entire body. And so, it is your cardiovascular system is what we call a closed circuit. So we do have, this is kind of fun, we have a closed vascular system as human beings. And what I mean by that is like the way that blood moves around our body is through a series of like tubes. And those tubes are all connected at some point. There's no open parts to it at the end, right? Like, you think about like your hose, right? That's kind of pumping blood around as well, but like it kind of comes out at the end and just kind of splashes everywhere, right? And that's how like a hose would work, right? It would be empty at one end and be pumped from another. But that's not how our vascular system works. Our vascular system is actually closed. So like it would pump, but then like go to another area and get sucked back in, and it's all interconnected. This is actually one of the reasons why it is so important for us to understand how blood pressure works, because of this series of closed tubes. Now, not every animal, by the way, has a closed vascular system. Scary a little bit, but spiders, they actually have an open vascular system. Which is actually one of the things that allows like if you look at the difference here, right? So like a closed circulatory or closed vascular system looks like this, right? Like these tubes, which we would call capillaries, basically kind of cover all of our cells. And then blood never really leaves those tubes. It's just able to kind of push things through the wall, right? Whereas like an open circulatory system actually has the ability to kind of splash blood, and then it just kind of gets picked up again and taken back to the heart. That works really well if you've got like a really tiny body with a heart literally dead center in that body, where it can just kind of splash blood anywhere it needs to go. And if you don't need a constant, very heavy supply of oxygen, that's going to work pretty well for you. But we're a little bit more complicated than most insects. So we have a closed vascular system. Now, disadvantages to a closed vascular system is that it does require us to maintain constant pressure evenly throughout the body. So if we create an area of high pressure in one place, it creates an area of low pressure elsewhere, which is not so great. And that's one of the advantages to an open vascular system. This is actually why, and I'm sorry to do this to everyone, because I'm going to ruin this forever, but like Spider-Man could never actually exist. So sorry, because he's my favorite superhero as well. I know. But the thing is, if we were ever to swing the way Spider-Man swings, it would create areas of super high pressure in the legs. And all of our blood would pool in our legs. And then all of a sudden there would be no oxygen to the brain. And we'd basically pass out right about here. And then just go flying off and, you know, like land abruptly somewhere else. And that's the disadvantage to a closed vascular system. So obviously it's going to be very important, right, for us to understand how pressure works. Because like if we create those areas of high pressure, it creates areas of low pressure elsewhere. And that is going to make life very difficult for all of us. Now, all of this pressure is going to start at our centralmost cardiovascular organ, the heart. So let's go ahead and talk about how this heart is generating pressure, because that's what's really going to be important here, right? So first, the heart is very muscular. It is made up of cardiac muscle fibers, which, like I said earlier, is the most type 1 fiber. In fact, I call them type 1/2. You know, it's like truly very, very intensely enduring fibers, right? Now, what's really cool about your cardiac muscle is that it's very involuntary. It has some similar characteristics to muscle, you know, to skeletal muscle, like we talked about yesterday. You know, you're going to see overlapping fibers of actin and myosin. And when they contract, it squeezes the heart. So just like we saw in a muscle, right? The actin and the myosin, they create cross bridges, and then, you know, myosin pulls this way, and the whole muscle fiber shortens. The same thing happens in your heart muscles, but they're much, much, much more tightly connected. In fact, if we look at skeletal versus cardiac muscle, you will actually notice they're way, way, way more tightly packed, right? So take a look at these under a microscope here, and look at how like tightly packed these fibers are in this cardiac muscle versus how sort of widely packed they are in skeletal muscle. Now, if we also zoomed in a little bit differently, I'm going to pull up a drawing version of this because it'll be a little bit easier to see. But you'll, what the, oh, I downloaded it. That's not what I want. Just open the image. If you look at like skeletal muscle, take a look right here. See how like it's got these really large kind of stripes on it? That's where you're seeing like all the individual muscle fibers. So that is how one of the ways that we can tell this is probably going to be able to contract a lot harder than a heart muscle can. You know, we can lift weights with this muscle. You know, I can grab a 30, 40 pound dumbbell with muscle that looks like this because of all these like big stripes. That makes it much, much, much stronger. You're seeing large amounts of actin and myosin. So we're not going to see as much of that in cardiac muscle. I'm actually going to go over here. We're going to see way less of those stripes. So it's not going to be able to contract as hard. Like I'm not lifting a dumbbell with my heart, but look at how much more tightly packed it is. It looks very smooth almost, you know. You can actually see in a drawing version of this, right? Much larger, you know, actin and myosin cross bridges for stronger, heavier contractions. And then over here, we see not quite as many, right? Large like stripes there, but look at how all these fibers are actually connected. They're all like kind of intertwined. The important part about that is that's actually what allows the heart to stay in rhythm with all the other muscle fibers. So if you contract one muscle fiber, it's going to make it way better at contracting all of the other muscle fibers, right? Imagine if we're holding hands and somebody pulls on me over here, I'm going to pull on you, right? Because we are interconnected. And that's how our heart is so good at maintaining part of its rhythm, right? When one fiber contracts, really all of them contract. Now, we also talked a little bit about basic anatomy and how the nucleus in a cell is kind of like the brain of a cell, right? Well, take a look at skeletal muscle. Look at how many little brains there are here, right? Which makes sense because we need to recruit different numbers of motor units depending on how much strength we need, right? And then look over here, you can still see, yeah, there's going to be some nuclei here, but there's way less of them, right? See how there's just not as many nucleuses? Well, that also makes sense because, you know, the more people there are in a room, trying to make a decision, the more likely you are to end up with arguments, right? Too many cooks in the kitchen, right? That's fine in a skeletal muscle. But we, if it's like a muscle contracting, sure, if there's a little bit of argument there, maybe we lose a little bit of strength. But if the heart muscles start firing at different times, that's really dangerous, right? We don't want too many cooks in the kitchen when it comes to like our heart squeezing, because then we might get the top of our heart squeezing when the bottom of the heart is relaxing, or we get the rhythm out of whack there, and then all of a sudden with the rhythm out of whack, we can't generate or maintain that pressure. And that's really what our heart is mostly in charge of. So because of all that, this is one of the reasons why I said when we talk about our nervous system, your cardiac muscle is very involuntary. You don't want control over your heart, right? We want it to beat on its own, and like, we'll talk about that. Like people will be like, I don't know, I'm pretty good at relaxing and I know how to slow my heart rate down. And I'm like, yeah, you do have like the ability to control your psychology and your anxiety levels, right? And you do have like some capacity to think calming, it's like margaritas on the beach, puppies and kittens, like you can think of these like relaxing, calming, happy things, right? And yeah, it might slow your heart down, you're thinking Zen thoughts, right? Absolutely. That does not mean you have conscious control over your heart. Your heart is autonomic, right? In fact, actually, what is going to control your heart is this little node right here. Okay, so that is called your SA node, right? And that's actually going to be in charge of your rhythm. So we'll come back to that in just a second, but let's sort of catch up on the slides here. So like I said, cardiac muscle fibers, they're shorter, they're much more tightly connected than skeletal muscle fibers. And that enables when, your heart, when one fiber contracts, it's going to make the other ones contract, right? Because they're tied together. And then they all have sort of a built-in rhythm where they are all under the control of this little node right here that's called your SA node. We'll talk about that in just a second. And that rhythm is typically about 70 to 80 beats per minute. Like everybody should be relaxing right now at home, at least I'm assuming. I mean, Amber, you're obviously in the car, if you're heading somewhere, that's fine. But like, we all got kind of like, different things we're doing right now. But if you're relaxing, if you're chilling at home and you're fully at rest, your heart rate is probably around 70 to 80 beats right now, right? According to my heart rate monitor, I'm at exactly 70 beats actually. And I'm a little animated, I'm like moving around a little bit, talking and stuff. But I'm not doing anything, intense right now. Now, obviously, if I start using muscle mass, or if I start using like different parts of my body, to squat or to walk up and down, to do stuff, right? If I start doing anything, well, then I'm recruiting more muscle, right? And then that muscle is going to need energy. So that means that it's going to need oxygen in order to output the energy that it needs in order to be able to continue contracting. So then all of a sudden, right, I start exercising. And what's going to happen is like any glucose that happens to be stored in my muscle mass will get burnt up as energy, right? We call that glycogen, by the way, the stored glucose. So glycogen starts to get burnt out. My muscles start to output energy, right? The byproduct of that is that their temperature increases a little bit, but also the big byproduct is like there's a lot of lactic acid, being produced as a byproduct of that energy production. So now lactic acid starts leaking into my blood. Maybe it's from my calves, but either way, it's going to eventually get to my heart. And when that lactic acid runs past that little node that we talked about, that little SA node, which, by the way, the SA node, we'll talk about this in just a second, but it lives right here. It lives in this little chamber right here. That's called your right atrium. And so as the SA node experiences this really acidic blood, it's like, ooh, like it's like somebody has started exercising, right? What'll happen is my nervous system, which that's what the SA node is actually part of, by the way. It's a sensory information, right? Goes up to my brain and my brain goes, oh, we must be doing exercise. We must be working. Got it. So then it'll send a signal back to the heart to increase the rhythm. And that is how your heart matches the amount of like work that you're doing. It's also why it's not exactly like super fast sometimes, you know, like when you start exercising, sometimes it feels like it's like, you know, it's like a car that's like flooded. It's like, and then eventually like, and you get that like little bit of like, you know, you get some lactic acid comes out in your spit and you're like, you know, you get that first loogie out of the way. Sorry. But like, you know, when you go for a run, right? Like that first like 2 minutes, it feels like you're like, you know, and then eventually you're up and running and it's like, okay, now I'm good, you know? But that kind of takes a little bit of time to kick in. This isn't the fastest thing in the world. Again, one more reason why it's so important to not skip your warm-ups. And I'm saying that to you with this face, but I'm also saying it to me with this face because I like to skip my warm-ups too. But like that's what's so important, right? We need to kind of like work our way in. So let's go ahead and quickly just talk about like how that nervous system control works, right? So you have what's called a conduction system in your heart. It's actually a much better, this is one of the things about this PowerPoint that drives me a little crazy, but like the picture of it is here and then my slides are here. So we're going to use this because I got the notes over here. So you can actually see, right, this little node right here, that's called your sinoatrial node, or it's called your SA node. Much more commonly, we're going to refer to the SA node as the pacemaker of the heart, okay? If any of you guys are familiar, if you've ever had like a grandparent or something who's had a pacemaker, so a pacemaker is actually like something that doctors can implant. It looks like this. And there's two versions of it. Usually they'll do like they call this one a subdermal implant, and they implant it under the skin. And it just kind of lives there. And what it does is basically, I'm trying to remember, there was a cartoon that actually was perfect, but it was like, basically it's there to make sure that your heart never falls asleep. It never gets out of rhythm, right? You know, it's like, whenever like your heart kind of like misses a beat or slows down, the pacemaker basically goes, hey, right? And it wakes it back up. It's like, oh, okay. You know, like, and it gets back on the job. So your SA node is supposed to do that naturally. It's the actual pacemaker that you're born with, right? And it's full of what we call pacemaker cells, actually. And their job is to have this kind of built-in rhythm that tells your heart when to contract. So this actually initiates the electric signal that runs across your heart, okay? So it's responsible for controlling your heart's rhythm. It lives right here in the right atrium. You're going to see, we're going to talk about the 4 chambers of the heart today. We got 2 atriums up top. We got a right atrium and a left atrium. Really quickly, just so I can address this now, for those of you who are, this is your first time hearing heart stuff, you will notice that I am pointing to the left side of the picture, and I called this the right atrium, and then I'm pointing to the right side of the picture, and I called that the left atrium. That is because this is labeled from the perspective of whose heart it is, right? So my right atrium is on my right side, and yeah, that's to the left for you guys, right? Actually, wait a minute. Don't I have my camera? I have my camera flipped around, actually. So it is mirroring for you. Sorry. So that is probably actually somewhat confusing. But yes, my right atrium is on my right, which would be your left, right? And the same thing is true here. Fun fact, I missed that sentence when I was initially in school learning about the heart, and was confused, probably late for class or probably missed a class or something, and was confused for like a whole semester until one day it just kind of, I like clicked for me and I was like, crap. So it's been a whole semester confused about the heart before I finally got it. But yes, this is the right atrium there, and this is the left atrium. So the right atrium is where your SA node lives. Now you'll notice, look at these little wires here, right? You'll notice that there's a like, it really does, it kind of looks like wires, right? And those are called internodal pathways, and their job is to allow an electric signal to run across these fibers of the heart. Now, what's interesting is there's this little like, you know, bundle down here, right? What's this little node right here? Well, that's called your AV node. That's your atrioventricular node. It's basically right at the border between the right atrium and the right ventricle. And what's interesting about that node is that is actually there to delay the signal that the SA node creates, which seems kind of weird because you're like, wait, we want this signal, right? We want the electricity to run through the heart so that my heart can beat, right? Because remember, it takes electricity to cause a muscle to contract. We saw that yesterday, right? The neuron to neuron to neuron. Eventually, a neuron interacts with a muscle fiber, runs an electric signal across that muscle fiber, and that's what triggers the release of calcium to trigger the contraction. Same thing's happening here. It's just that it's happening directly with the SA node. You can think of the SA node almost as a giant neuron, right? Creating a giant little zap, right? That node right there starts the signal, and then this node delays it. Why would we want to delay the signal? Well, that is to allow the top chambers of the heart to finish contracting before the bottom chambers of the heart contract. And that's why, let's go ahead and look up what the heart actually looks like here. I always love looking up heartbeat GIF because it's like, this is obviously not what I mean. Although that is how I like to draw hearts. I can't draw an actual human heart. It's so difficult. So I always draw like Valentine's hearts. But we'll actually take a look at this. This is actually what the heartbeat really kind of looks like. You'll notice the top of it finishes contracting. It sort of goes like this. It goes boom, 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 boom. 1, 2, 3, 4, right? Lub, dub, right? And that's kind of what we hear in a heartbeat. You lay your ear on somebody's chest, you're going to hear lub, dub, lub, dub, lub, dub, right? And what that is you're actually hearing the chambers inside of the heart either open or slam shut, right? So you're either seeing like the atriums or you're hearing the atriums or the ventricles like opening and closing. So when the SA node starts the signal, what'll happen is it'll run off of these top fibers first. That allows that to start contracting. Hits the AV node. The AV node pauses it for just a second. Then the signal continues traveling down. These muscles start to relax as these contract. And that is how we are going to drive blood into the top of the heart first. Then it will allow it to drop into the bottom of the heart. Then this part will contract and that will eject the blood out of the heart. So what's happening is the SA node starts the signal, the AV node delays it for just a second, and then eventually it moves to all these other fibers here. This right here, these are called your Purkinje fibers. And then there's this really big bundle here called the bundle of His, which sounds like a sci-fi alien, you know, or it sounds like a Harry Potter novel, like the Harry Potter and the bundle of His. You know, but like that's what this like big bundle is at the very bottom as it spreads throughout the heart there. So what I want you to know, and the one that you'll probably be tested on, the one that NASA typically tends to ask about is just the SA node. You actually don't need to know, have those other ones. You're probably not going to get a question about like how the AV node delays the signal or how the bundle of His works. But I like to mention it because like it does make a lot of sense when you look at this like bump, 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 bump part of your heartbeat, right? Because that is going to be very important for us to understand how pressure is driving blood throughout the body. If your entire heart squeezed all at once, it would basically just create a lot of pressure and blood would be going towards the heart and then it would get pushed back away and it would get pushed back away. But by going like this, when this opens up, blood goes rushing in. And then because this is still squeezed, blood can't go any further. So then all of a sudden, this starts to open up, which is now an area of low pressure. So blood rushes in there. Meanwhile, this part starts to squeeze again, and that keeps it from backflowing this way. And then this squeezes, right? And then it goes out of the heart. So that keeps blood from backflowing. So understanding that signal delay is kind of important because it helps us understand why blood moves the direction that it does. But you probably won't get a multiple choice question about that. Chances are what you'll get a question, and I think this is even in your homework, but they'll say blank is the pacemaker of the heart. And then you'll have 4 options, you know, it'll be AV node, bundle of His, I don't know, some other dummy answer like a totally fake one. Usually the way multiple choice works is it's like one really close answer. It's like the correct answer, a really close answer, an opposite answer, and then usually just like a rando. So So it's like the opposite of the SA node would be, I don't know, something completely different, like call it something in the respiratory system. We'll say like an arterial. That's a blood vessel thing too. But and then the AV node would be like the close answer, right? And then like a totally random one, you know, I don't know, type 2 muscle fiber. And then the right answer, which would be the SA node is the pacemaker of the heart. So that is sort of the conduction system portion. And then let me just show you really quickly how that signal actually sort of travels. Let's see if I can find a picture of this. There we go. So you can actually see this GIF runs a little quickly, and I can't really slow it down, but you can see it kind of runs across the top first, delays it, and then runs to the bottom. And you can even see there's actually different ways, like this dark, right? That's where the heart is kind of filling, right? So the top fills, and then it ejects it out, right? So top empties, pushes it out. It's a little quick moving. Oh, there we go. There's a bit of a slower image, right? But yeah, and then you can see blood is kind of moving in, and then it moves down, and then it gets pumped out, right? And that is the pressure generation. And pressure is really what's important here. In fact, we're going to kind of spend today talking about 2 types of pressure. We're going to talking about like blood pressure, right? But we're also going to be talking about like concentration pressure. When there's like a really high concentration of stuff in one place and a very low concentration in the other, stuff wants to move. You know, if all of us in this Zoom call right now, we're all crammed into a closet together, pretty sure someone's going to want to leave, right? Like, it's like, this is a lot of pressure in here, right? And it's like, I'm just going to scooch this way, you know, like, yeah, I don't love a crowd, you know, love people. I see myself as a bit of an extrovert. Don't love a crowd though. So, yeah, that's kind of how pressure is going to work. We're always going to seek an area of low pressure. So any questions so far on that conduction system? Does all the electric part of this conversation make sense, guys?
It does. When someone gets, like, say they have to, I forget the name of it, but when they have to be shocked, does it like,
yeah,
like, does it have like the same effect or help? You know what I mean?
Kind of. So here's what's fun about defibrillators. Yeah, you see it in TV, like glare, you know, and then like they do the thing, right? And that's, by the way, that's actually fiction. You actually don't typically see as much of that, like, you know, you always see it in movies where they like zap them and then their body goes, and they jump off the table. That's meant to represent that, like, yeah, electricity is running through the body, so it's making their muscles fire. Doesn't quite happen that way, but so the way a defibrillator works, and this is what's kind of fun, right? You think of like an AE, and you'll have those, like, you'll have to learn how to use those to get your CPR certification, right? So what they'll teach you is that, like, yeah, it's kind of restarting the heart, right? Like, it's starting the heart back up. But fun. Oh, did we just lose her? It was her question, and then she, oh no, I think she got booted out of the call. She got a drop connection. Let's give her 1 second here. That's the worst. And then we'll get her back in. Sorry, guys, 1 sec. Any other questions while we're waiting? Well, by the way, morning, Marjan. I didn't get the chance to say hi to you. You missed all the drama this morning. My friggin' speakers crapped out on me and we had to restart the call. So you really didn't miss much today, by the way. But I am glad that you made it in. I love the interesting way that we have learned how to communicate on Zoom sometimes. Like it's almost like hieroglyphics. It's like emoji speak.
Yeah.
Oh, come on, Amber, get back here.
Well, last night, one of my friends cut his finger. So I had to take him to an ER, and you know, it was like too late. By the time I got home, it was just like,
Oh,
I think it was like 3 o'clock in the morning.
oh,
So
that's rough. Can I tell
yeah.
you, when you said that it was too late and you were talking about like I thought, I was like, it was too late to reattach. I thought you were going to say it was too late to reattach his finger. And I was going to go, oh no.
Oh no.
Okay.
Sorry.
Well, that's still rough,
Honestly,
but
Sorry,
yeah.
my phone got too hot. It kind of just shut
yeah,
off.
no sweat. Yeah, we waited. So the way a defibrillator works, here it is. So a lot of people think that your heart has stopped. And so we use the defibrillator to restart the heart. Fun fact, that is actually not quite what's happening in a defibrillator. What your heart is experiencing is, remember how I said we don't want the heart fibers to contract randomly? So fibrillation is where your heart is actually quivering. All the fibers have kind of taken off on their own and they're all squeezing all at once. So it's not pumping blood around the body anymore. It's kind of just like pumping it forward and back, and it's just kind of like randomly, like blood's probably just going like this into and out of the heart, rather than like going in and going out and then coming back in and going out. Now it's just kind of going everywhere all at once. Your heart's kind of sucking blood back towards itself because it's quivering randomly. So what we need to do is we need the SA node to like take control and be like, everybody shut up, I'm in charge, and then take control and like get blood to where it needs to go, right? So rather than fibrillating or quivering, right, what we do is we run a massive amount of electricity through the heart suddenly. And what happens is like, you know, clear, and it zaps them, right? And what that does is it sends so much electricity through all of the heart that the entire heart stops for a second and we shut it down. And that allows the SA node to be like, all right, everybody's nice and quiet. This is the rhythm. And then it gets back onto a normal rhythm. So what's weird about those defibrillators, they don't start the heart. They in fact stop your heart, weirdly enough, which allows your heart to then restart its own rhythm, its own pace. And that gets it to start pumping blood again, and then it functions and can save somebody's life. But that's what's happening. Yeah, it's basically we're running such a massive amount of electricity that it allows the SA node to get control of the heart again. So in a way, yes, it does start your heart back up, or at least it gets your heart to start functioning properly again. But weirdly, it's actually kind of shutting it down for just a second. You know, it's kind of like, you know, my computer was being a jerk 20 minutes ago. So what do? Freaking restarted the thing, you know? I shut it down for just a second. That's kind of what the defibrillator actually does. Okay, so let's go ahead and look at these chambers of the heart. Let's talk about like how blood flows from chamber to chamber to chamber. So there's two ways that we're going to break this down because it's a 4-box situation here, right? So if we can think about it, the way I honestly like to picture the heart, you know, we could draw a Valentine's Day heart here and, you know, put 4 chambers in it, and it would look something kind of like this. But the way I kind of like to think about it is honestly just like this. Right? If this is meant to represent the various chambers of the heart, right? Let's go ahead and say that we've got like a left side, right? So this is going to be the left side of the heart here on the right of the picture. And this is so the left side. And then we'll put the right side over here. So we are going to have 2 sides to the heart, the left and the right. And then we are also going to have 2 types of chambers. We're going to have the top and the bottom, which are going to be your ventricles versus your atriums, right? So this is going to be the atriums. So we'll say atria, that's the plural for atriums. And then over here, we'll have ventricles, okay? And so ventricles are representing the chambers on the bottom, and the atriums are representing the chambers on the top. So that's kind of how our hearts actually function. Now, obviously, I put some of this in color and I put some of this in black and white, and that's because you know, they're going to be different depending on where they're at, right? So what is an atrium? Okay. Well, if I Google atrium, you'll actually notice I get a bunch of pictures of like, you know, big open spaces, right? They're usually like the gathering lobby of like a motel or, you know, like a big old fancy building. I mean, look at all these big fancy atriums that we're seeing here, right? So an atrium is a big empty gathering place, right? So in your heart, that is still very true. This is basically where we gather blood as it's returning back to the heart. So what are the two places that blood go inside your body? Well, obviously blood's got to deliver oxygen to the various tissues throughout the body. So blood goes everywhere. Goes up to your brain, goes to your muscles, goes to your organs, whatever, right? And then there's also like, it's got to come back. The other place that it goes is to the lungs, right? So atriums are going to gather blood that's either coming back after it's been done delivering oxygen to the body, or an atrium is going to gather blood once it has just picked up oxygen from the lungs. So we got two atriums, and they're the ones on top, right? The right atrium, right over here, is responsible for gathering blood that has returned to the heart from the body, right? So your right atrium, we'll put that in blue here. And that's meant to represent that this is deoxygenated blood. Now, really quickly, just to dispel a myth, you never have blue blood. I heard that growing up. My parents told me that. You know, blood is actually blue until it, you know, when you cut yourself, it's exposed to the air, and that's what turns it red. At least that's what I was told when I was a kid. That's not true. Your blood's never blue. Your blood is always, always, always red. It's either a really, really dark red, or it's a really bright red. And that just means if it's really bright, it has a lot of oxygen in it. Because oxygen interacts with the iron in our blood, turns it a bright red color. When there's not very much oxygen in your blood, it is a super, 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 super dark, 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 dark red, which is why they always show that, like, and it wouldn't work this way in real life. But if you ever see like if you've ever like, you know, donated blood or seen blood, you know, go into like an IV, right, or from an IV like into a bag or something for donation, it's not really getting exposed to do very much air, so it kind of stays like kind of a dark-ish color, versus when you cut yourself, it's like, oh, there's a lot of oxygen in the atmosphere, so yeah, it looks like a very bright red color. So in this case, it's going to be super dark red. Yeah, question.
So where do they get this theory that the blood is blue?
So it is, so if you mix a super dark color of red with the pigment of like a pretty darn light colored skin, it kind of looks bluish, you know? It's just when you mix whatever this color is to, you know, dark red, it kind of comes out bluish. And that's kind of where it came from. Yeah. Not always true, but sometimes true. Looking. So yeah, that's kind of where, you know, and it does. I mean, like our veins looks, you know, sometimes you look at them and it looks bluish. So people just assume that it's like, oh, that's the color. But, you know, if you remember art class and you mix this with that, it kind of comes out in different pigments, you know? Right side of the heart, right? This is our right atrium. So we're going to write this in blue because it is meant to represent deoxygenated blood. So that's actually what blue is going to kind of represent in, you know, textbooks and stuff like that. It represents deoxygenated blood or blood that has given up all of its oxygen, right? It's full of carbon dioxide. So the right atrium is responsible for gathering deoxygenated, I'll say deoxygenated blood as it returns from the body. Okay, so this is blood that has, you know, gone out and delivered all of its oxygen. Right now, the left atrium, we're going to draw that in red here, right? This is also going to gather blood as it returns to the heart, but this is gathering it as it returns from the lungs. Now, it just got done coming from the lungs, which have a lot of oxygen in them. So the left atrium is super, super bright red, super highly oxygenated blood. Okay, so the left atrium is responsible responsible for gathering oxygenated blood as it returns from the lungs. So again, our heart is going to gather blood as it returns from two key areas. It's either going to come from the entire body, getting back to the heart. So like if it goes to my brain and it gets back to the heart, if it goes to my muscles and gets back to the heart, right? That's the right atrium. Because it went to the brain or because it went to the muscles, it dropped off all of its oxygen to keep those cells alive, right? So now the other side of that is the left atrium. If blood has gone to my lungs and dropped off all of its CO2 and picks up a bunch of oxygen, now it's a super bright red color, you know, just like when you cut yourself, right? So now it's going to come back to the heart. So this is highly oxygenated blood. And that's why we draw it in these colors, right? So this is deoxygenated. You can see this big tube here and this big tube here. This is called your vena cava. This is your top vena cava. This is your bottom vena cava, or your superior and inferior. And that's the vein that is returning back to the heart. This one's coming from the upper body. This one's coming from the lower body. So blood's going to dump into that right atrium there, and it doesn't have any oxygen in it because it already gave it up to all of our tissues. Now, what's going to happen is it's going to drop into this chamber here. That's our right ventricle. So we got our right ventricle and our left ventricle. Now, ventricles are responsible for pumping blood out of the heart. So they eject blood from the heart, okay? So ventricles are chambers that pump or eject blood out of the heart. So we've got our right ventricle attached to our right atrium. And this one is going to receive blood from the right atrium. So this is our right, whoops, that needs to be blue. This is our right ventricle, right? And it pumps deoxygenated blood out of the heart to the lungs, okay? So this is responsible for pumping all that low oxygen blood to a place where it can pick up a bunch of oxygen. It pumps it over to our lungs. Meanwhile, the left ventricle is going to pump oxygenated blood out of the heart to the body. So here's what I always tell people to do. If you're going to try to memorize the heart, right? Memorize what the overall categories do. Memorize what an atrium is, and then memorize what a ventricle is. Think of the word atrium. It's a gathering site, right? You walk into the atrium of a lobby of a motel, of a, I don't know, skyscraper or something like that, right? Couldn't think of the word building. Speaking of low oxygen. So that's what an atrium does, right? It gathers blood in an area, right? And then a ventricle pumps blood, right? It vents blood out of something, right? So it's venting it out of the heart. So just remember that first. Then memorize one chamber of the heart. Because if you can remember those two rules and then you memorize one chamber, it will help you memorize the rest of the heart. So the chamber that I recommend memorizing is this one right here, the left ventricle. The left ventricle is probably the most relevant of the chambers to us as trainers because it's actually where you're measuring pulse. So when you take two fingers and you measure someone's pulse, either, you know, here on the side of the neck or you do it on the wrist, right? The way that works is you are actually feeling blood pump throughout the body. You are feeling your left ventricle contract. So when your left ventricle contracts and it goes rushing past, you can feel it, right? And that's your pulse. So the left ventricle pumps oxygenated blood through out out the heart. It should say out of the heart. God dang it. Out of the heart to the body. Let's see if I can just fix that.
I hope not.
Right, just pumps it out the heart. That'll work. So it pumps oxygenated blood out of the heart throughout the body, right? And you're feeling it. You can feel it as it goes rushing past, right? So now, if you remember our overall rules, right? Now you can just sort of like logic puzzle your way to remember all the other chambers, right? If I remember that the left ventricle pumps blood throughout the body, well, then obviously my right ventricle pumps it to the lungs. So I used the opposite to remember what the other one does, right? And then, you know, if I remember what left is, I can remember what right is. I remember what up is, I can remember what down is. Yin to yang, you know what I mean? Lex Luthor to Superman. So then if I remember that my left atrium, or if I remember my left ventricle, you know, pumps blood, then I can remember that my left atrium gathers blood. And if my left atrium gathers blood, you know, that's, you know, going eventually to attach to my left ventricle, the ventricle is going to pump it to the body. Therefore, I know it must be oxygenated blood. So the left atrium is gathering blood that returns from the lungs because it's oxygenated, which means my right atrium must be gathering deoxygenated blood. So if I can remember this one corner of this little box right here, little logic box, you know, I can remember the other three boxes naturally, as long as I remember my general principles, okay? So that's the chambers of the heart. So now let's go ahead and go and let's go through a cycle of blood a couple times through the body here, right? So what I want you to remember is I want you to remember where this is going to go, right? So let's just say, for the sake of argument, we got a brand new red blood cell. This red blood cell enters the world for the first time. It's never existed before, you know, made in some part of your skeletal system, because that's where your blood is made, actually. And it's going to go ahead and start here in the bone, and then it enters the bloodstream. It's never gathered oxygen before. It's brand new to the world. So the first thing it needs to do is it needs to get over the lungs to pick up oxygen. So it enters the bloodstream. And so the first place it's going to go is right over here to the right atrium. Okay, it's going to get gathered by the heart first. Then it'll drop into the right ventricle, where it will get pumped over to the lungs. Now, for the very first time, it's going to pick up oxygen. And now that it has like a lot of oxygen in it, what it's going to do is it's going to make its way over to the left atrium. And then from there, it's going to go into the left ventricle. Then it's going to get pumped out to the body, right? Somewhere, you know, over this way, right? And then it'll deliver that oxygen for the very first time. Then it'll eventually work its way back. It'll come right back into that right atrium, go into the right ventricle, get pumped over to the lungs, right? And it'll just kind of slow, I don't know what those arrows are supposed to help, but that's how it's going to work, right? This brand new blood cell is going to go from heart to lungs to heart to body to heart to lungs to heart to body to heart to lungs to heart to body, until eventually it gets all worn out. And then eventually one day it's so worn out that the liver notices that it's not picking up oxygen anymore. And then your liver is going to go and eat it. Fun fact, that's actually where all your red blood cells end up. There's this part of your liver called, coolest name in anatomy, by the way, the red blood cell graveyard. And that's where your liver basically destroys it, takes all the iron, takes all the proteins out of it, and then sends it over to your bones so it can be born into a new red blood cell. And that cycle kind of repeats for your entire life, which is kind of fun. So heart to lungs to heart to body to heart to lungs to heart to body, until eventually it's all worn out. So again, getting specific about those chambers: right atrium to right ventricle to lungs to left atrium to left ventricle to body. Right atrium, right ventricle, lungs, left atrium, left ventricle, body. And that is the entire cardiac cycle. That is how it's working. And I got that written right down here. Again, right atrium to right ventricle to lungs, left atrium to left ventricle to body, back to right atrium. I should just say, and repeat. Okay, so it is a cycle, nonstop. So it's sort of a double figure eight, if you want to think of it that way. So each contraction of the ventricle pushes blood from the heart into either the body or the lungs. And then the amount of that blood is what's very important to us. That's actually what we are going to try to measure when we are doing fitness assessments. And that's how we're going to measure the function of someone's heart. How effective are they at pumping this blood around? So that's the anatomy so far. Any questions on those chambers or any questions on that blood flow, guys?
As far as like where acid comes from, does it go through the right atrium, since there's since the air goes through the left mostly? So
remember, like that air is so that air is carried by the red blood cells themselves. So the lactic acid that I was talking about earlier, there's going to be lactic acid in the blood. It's just going to kind of passively get picked up in your blood. One thing that we have not covered just yet, but blood is actually made up of a lot of different things. If you look at, let's see, the components of blood, most of it's water. Actually, most of your blood is water, but it actually looks something kind of like this. So this plasma here is mostly water, but it's going to have like other stuff in it as well. Vitamins, minerals, proteins, fats, carbs. Those things are going to kind of be suspended in here. Glycogen, like sugar and stuff, like that's the carbs living in there. And then you get your white blood cells. That's your immune system in this little section here. And then the red blood cells are actually carrying the oxygen itself. So oxygen's in the red blood cells. But this section here, there's going to be some lactic acid flowing around in some of that water, mixed with some of that water. When that runs by the SA node right here, which is in the right atrium, that's how your heart, that's how your nervous system learns that, oh, the blood is very acidic, we must be exercising right now. And that's what speeds up your heart rate. It's also running past other sensory nodes. I don't want to make it sound like it's only the heart that runs by. It's also running through parts of your brain because there's blood flowing through your brain, obviously. And when that lactic acid runs up here, your brain goes, oh, I need to pick up the breathing rate as well. And that's what speeds up your diaphragm and makes you start breathing harder. And that's how like your heart and your lungs kind of match with one another. It's because all of it's under the control of your nervous system. And then there's other ones, there's some in your stomach even. And that's kind of how all of this is sort of like maintaining rhythm. Because obviously when your heart rate speeds up, your breathing rate speeds up as well, and this is why exercise can sometimes cause you to feel a little nauseous, or maybe even dizzy sometimes, is because like if all of that happens and it's not in rhythm, it can, kind of make you feel a little icky sometimes because your body's out of sync. So what we tell people to do, hey, go back, lower the intensity of your workout. If you just jumped into workout really fast, you didn't warm up properly, you're going to get those kind of nasty feelings. So ease it back and then ease yourself back up, and chances are you'll feel just fine by the time you get nice and warmed up, hopefully, unless you have like, some type of dysfunction. So that is the sort of overall like process of the heart, but let's look at how it actually functions, because that's what we need to understand, right? So the function of the heart, what we're going to kind of pay attention to and measure is what we call our cardiac output. Okay, so your cardiac output is the overall performance of the heart. Now, this is probably the most important concept of the day. It's not the hardest to understand. We spend most of our time kind of talking about those heart chambers, and then we'll spend a bunch of time looking at like our blood vessels and stuff, because those are kind of the hardest to memorize. But if I had to like put a finger on what is the most important concept of the day, I would say that this is it right here. So cardiac output is the overall performance of your heart. Like the way we measure how well your heart is working, two things, right? It's your heart rate. So a heart that can beat faster is obviously a more effective heart, right? It can pump faster, right? Just like if you were running, whoever can, step the quickest is going to travel the fastest, right? So that's kind of what's happening in the heart, right? We want a heart that is able to beat often. The other thing is we also want a heart that can squeeze really hard. You look at two people who are lifting a bunch of weight. Whoever can lift the most weight is the strongest, right? Well, the heart that can squeeze the hardest is going to pump the most blood. So therefore, that's a very efficient heart. So your overall performance is two things. It's your heart rate, that's how often your heart is beating, times your stroke volume, the amount of blood ejected by the heart per beat. So the volume of blood ejected per beat multiplied by the number of beats in 60 seconds, okay? So let's say you're pumping, we'll make up a fake number here, 10 units of blood every time your heart beats, right? And you need to deliver because you are doing 100 units of work. Therefore, if you're pumping 10 units of blood every time and you're doing 100 units of work, you need your heart to beat 10 times to deliver that oxygen, okay? Now, let's say your heart isn't that effective. Let's say in our example that it's only able to pump 5 units of blood every time it beats. It's not as strong as the person next to you, right? So you're pumping 5 units of blood, they're pumping 10 units of blood, and you both need 100 units in order to do the amount of work to walk up a hill, right? You're both walking up the same hill. You need 100 units of blood. Well, this person's getting it done in 10 beats. You're getting it done in 20 beats. So your heart speeds up in response, okay? This is why when we're exercising, our heart rate starts racing because we can only pump so much blood every time we beat, right? So let's just say for the sake of argument, Eric, you and I are in a race, okay? We're going to race each other, and it's a very unique race. Weirdly enough, we're not seeing who's the fastest. What we're actually going to measure, we're both going to go 1 mile, and we're both going to do it on a treadmill at 6 miles per hour. So in this very weird race that you and I are running, we're both going to finish at the same time. But what we are testing is what your heart rate is at the end of that 1 mile and what my heart rate is at the end of that 1 mile. So we both run the same distance. We both run it in exactly the same length of time. But when we're done testing, your heart rate is 120 beats per minute, okay? And when we're done testing, my heart rate is 160 beats per minute. So what does that tell us? That tells us that your heart is much more efficient than mine was because it was able to do the same amount of work in less beats. So you're in better shape than I am, right? And that's how our fitness assessments are going to work, right? And we know that that's true because it's going to be impossible, guys, for us to be able to measure someone's stroke volume in the gym. Like I can't like hook you up. I mean, I could. We actually have ways of measuring stroke volume, but I don't have access to it in the gym. Plus I don't want to. There's sweat and germs and,
that was wild.
Yeah, right. I don't know about you guys, but I don't want my blood exposed at the gym. Right? So what I can measure though, is I know that this formula exists, right? So I can measure my heart rate. I can measure your heart rate. And so if I see that my heart rate's really high and your heart rate's really low, and we both did the same amount of work, that tells me that my stroke volume is not as good as yours. So cardiac output, which means my cardiac output's not as good. The overall performance of the heart, it's your heart rate times your stroke volume. There's a little bit of like, we're kind of doing a little bit of algebra here, right? Because I know this, but I don't know this, and I'm trying to figure out this, right? So it's the volume of blood ejected by the heart per minute, okay? And so your cardiac output, which we label as Q, by the way, I know it's kind of confusing, but it's Q stands for the quotient. And so the quotient of the heart is the heart rate times the stroke volume. So Q equals HR times SV. I don't think they ask you that question anymore. They did when I got tested like years ago. I had to like know, they'd be like, what does this formula represent? And then 4 questions. I don't think they do that anymore, but I still put it in here just in case they do someday. But what they will ask you 100%, guys, and this is what always confuses people, is they get their definitions backwards. They will either ask you what the overall performance of the heart is, which is the cardiac output, or they'll say the volume of blood ejected by the heart per beat is, and then that's stroke volume, or they'll say the rate at which the heart beats, which is the heart rate, or the number of beats in 60 seconds represents the, and then that's heartbeat. So you may get any variation of that. So you do need to know all 3 parts of this formula, even though I don't think they'll ask you like the Q equals, and then it'll be like blank and you got to finish it. They won't ask it like that, but they will ask you any of those 3 definitions. Stroke volume, that's the amount of blood per beat. Heart rate, that's the number of beats in 1 minute. And cardiac output is those 2 things multiplied together. Overall performance, right? I always like to use the analogy, we're going to say, you see this formula later. The formula for speed is stride distance times stride rate equals speed, right? It's kind of the same thing with your heart. Stroke volume times heart rate equals performance, right? If I can take it faster steps than you, I might be a little quicker, unless I'm not covering very much distance. If I'm not covering very much ground, then I'm not going to be faster. If I'm like, but I'm traveling 1 inch every time, that's not very good, right? Which is why we're going to talk about in the sports class. I'm getting ahead of myself. I probably shouldn't do this. But when we get to the sports class, we're going to look at like the concept of like overstriding, like taking too big of a step slows your steps down, but understriding speeds up your step rate, but then you're not covering any distance. So speed is kind of a perfect mixture of the 2. Same thing is true of your heart rate. So we're going to measure our heart rate. And the way NASM is going to encourage you to do it, they do like the radial pulse. They like 2 fingers in line with the thumb and index finger of the left arm, just above the wrist. So actually kind of right where my watch is, but right here. That is sort of, that's where we want to do it. You should be able to feel your pulse there. 2 fingers just in line with the thumb and index finger here, just above the wrist. And that's where you should feel it. Some people, if you do have a hard time with that, some people will have a slightly weaker feeling pulse. Doesn't mean much, by the way, if you're freaking out about that. But if you do have a trouble feeling that, you can always also go 2 fingers just to the side of the trachea there, near the Adam's apple, and that is your oh my god, I'm forgetting the name of it. Carotid pulse. That's your carotid artery. So either radial at your radius here or carotid artery. Both those arteries are going to be really effective. So now, the way NASM is going to recommend it, if you're in the middle of a workout, you want to know what your pulse is and you don't have a heart rate monitor, do it for 6 seconds and just count the number of beats in that 6 seconds, and then just add a 0, because 6 times 10 is 60 seconds. That's your pulse. So if you do it 17 times in 6 seconds, then your heart rate is currently 170 beats per minute. And that's how you can monitor your heart rate mid-workout.
Is it also true you can count to 15? Like, yep. Well, not count to 15. Well, you know what I'm trying to say.
Yep. 15 times 4. Yeah.
Times 4. Okay.
So whatever you do, just get it to 60 seconds. 15 times 4, 6 times 10, 60 times 1. You know, like you just do a full 60 seconds. That works too. But we like the 6 times 10 version because if you're in the middle of a workout, like imagine you're jogging, right? It's just very difficult to like hold it for a full 60 seconds. So you're probably going to slow down. So 6 times 10 is the most convenient mid-workout. We actually don't use that formula very often. Like if you're doing an actual fitness assessment, you're probably in a resting situation, which means you're probably just going to do a full 60 seconds because you're resting. You know, it doesn't matter. You're not worried about, you know, interrupting the workout. They're at rest. So, all right, let's go ahead and talk about blood. Blood's a little quicker. Blood, like I said earlier, it's made up of a couple different things. Most of it's water, about 55% of it, water with stuff in it. Like if we look at actually, let's see here, plasma. The thing is, this is going to be difficult to look up percentage wise because everybody's plasma is going to be a little bit different. Most of it is water, but if you're dehydrated, then some of it's going to be protein, and some of it's going to be sodium and potassium. But if you don't have enough electrolytes, well, then there's not a lot of sodium and potassium. So I don't know. We're not really going to see the components of what that makes up, but some of it's gases. A lot of those dissolved gases are CO2, a little bit of oxygen in there. But electrolytes, proteins, carbs, most of it's water. And then the red blood cells are about 45% of your blood. And then just a little bit of it is your immune system. That's your white blood cells and your platelets and stuff, which help you clot if you need to. So the big thing we want to remember about blood is, what its job is, right? So it acts as the medium to deliver and collect essential products from your body's tissues. Again, proteins, fats, and carbs. In the red blood cells in particular, though, there is a special protein. So in we call them erythrocytes, those are your red blood cells, there is a protein of what is called hemoglobin. And hemoglobin is a protein that is very good at binding to oxygen. And the reason why is because hemoglobin has a molecule of iron at its center. And iron and oxygen are actually pretty buddy-buddy. They get along really well. Iron and oxygen love to bind together. And you've actually seen that before. If you've ever gotten a little bit of metal wet and left it out, or if you got cast iron pans and you left too much water in them, iron and oxygen basically turns this bright red color. And that is why your red blood cells are red, is because there is a molecule of iron at the center. And so that is what's attracting the oxygen molecules, carrying it around. And so that's why, right? So hemoglobin is the protein present in our blood that binds to oxygen that allows those red blood cells to carry that oxygen around. And then eventually it'll get to a tissue and it'll be much more attracted to the tissue than it is to the red blood cell. So the oxygen will move into the cell and then it will actually attract carbon dioxide or CO2. Look at that formula, CO, that's the oxygen 2. So guess what? Red blood cells are also very attracted to CO2. And that's how a red blood cell will drop off oxygen to the tissues and pick up CO2 from those tissues before it gets to the lungs, where then it actually flips and it will drop off CO2 and pick up oxygen. And that's what we're going to be talking about when we get to the lungs here in just a moment. But obviously this has to have a way to travel, and that's where the final part of our cardiovascular system comes in, our blood vessels. So your blood vessels are all of these little tubes running throughout our body. If you guys ever get a chance, I know I always say this, but if you ever get a chance to go to the bodies exhibit, I highly recommend it. It is, I think, back actually. I think it's here right now. Yeah, and if you want to go to, is it Buena Park still? But it is very fascinating. It is, oh, maybe not. No, that was 2020. It might not be around right now because they travel around with it. But it is very cool. It is where they've basically, I think they call it plasticized different tissues of the human body. But here is your blood vessels, right? By the way, here's your nervous system kind of laid out. That's kind of fun. But look at all these blood vessels absolutely covering the various tissues throughout our body, right? Fascinating stuff. So it is a closed circuit of tubes, right? So blood vessels are this closed circuit of hollow tubes, and that allows blood vessels to travel to and from the heart, right? Some of the blood vessels are heading towards the heart, some of them are heading away. So we need to understand what that means. So here's the rule, guys. Black and white rule forever. Arteries are any blood vessel that travels away from the heart. That is their definition. Veins are any blood vessel that travels towards the heart. Now, most arteries are going to be a bright red color when we draw them, because if it's traveling away from the heart, it's going to deliver oxygen to wherever it's going. However, that is not true of what are called your pulmonary arteries. They're traveling away from the heart over to the lungs. That's the only moment where there's like a blue deoxygenated artery, is when it's got to get over to the lungs. Veins are always traveling back towards the heart. So veins are blood vessels that are generally blue in color because they are traveling towards the heart. You know, they just got done delivering oxygen to, you know, the legs, or I guess this is the kidneys, the spleen, the liver, whatever, wherever it happens to be. However, there are the ones coming from the lungs. So those are your pulmonary veins. They are bright red because, you know, they are headed, you know, they just got done picking up oxygen. So that rule of like, the way a lot of people learn this in like school early on is they'll be like, oh, arteries are red, veins are blue. And that is how you see them throughout the body. But that is not true in the lungs. It is flipped there. So do not pay attention to their color. What's important is their function. Arteries go away from the heart. Veins go towards the heart. Now they do branch smaller and smaller and smaller. You can actually see that here. If you look at this picture, there's a big old artery. That's actually called your aorta. Huge, about the size of a garden hose, actually. And then it splits, gets a little bit smaller, splits a little bit smaller, a little bit smaller, right? So a small version of an artery is called an arteriole. It's a blood vessel traveling away from the heart, but it's branched off from an artery. Oh, I deleted my definition of capillaries earlier. Whoops. I must have saved over that in the past. So those are arterioles. Capillaries are microscopic blood vessels that act as the exchange site of oxygen and nutrients in the body. I think that's the textbook definition. So arterioles will branch smaller and smaller and smaller and smaller off of the arteries, okay? So an arteriole is like a mini artery. And then eventually they'll become capillaries. Capillaries are little microscopic blood vessels. And what they do is they form these little beds. They form these like little beds that absolutely cover tissues. And that's actually how blood cells are able to interact with the various tissues of the body. So you can see these little tiny red blood cells here. By the way, red blood cells are some of the smallest cells you have in your body. Fun, weird sounding fact, your capillaries are sometimes smaller than the red blood cells. And that may sound impossible for a second because you're like, wait. How is the tube smaller than the thing that travels through the tube, right? Well, look at a red blood cell shape. Red blood cells have this little, they look like a little filled in donut, you know? They got like little, like kind of little donut shape. That actually allows them to fold in half. They can kind of squeeze themselves and fold. And so, I'm not sure if I can find a picture of this. Oh yeah, kind of. So you'll actually see them kind of bend and fold so that they can fit through these little itty bitty tiny blood vessels. So capillaries will actually be so small enough that the blood cell has to kind of fold itself to fit through. And what that does, it causes it to get blocked for a second. That creates pressure that causes it to shoot through. And that's actually one of the ways that we maintain blood pressure in our body, is by having our capillaries be small enough that the red blood cells are like, and then they pop through to the other side. That's kind of cool. It's actually one of my favorite parts of anatomy. So arteries are very large as it comes out of the heart, and then they get a little smaller, they become an arteriole, then they form a capillary bed, and eventually those capillaries will start to come together, and they'll get a little bit bigger as two tubes sort of match, and a little bit bigger as they start to come together, and they'll become what is known as a venule. And a venule is basically a small version of a vein. Because if a bunch of venules come together, you'll end up with an overall vein. And then that vein will come all the way back to the heart, and eventually it'll drop that blood back at the heart. So arteries are going away from the heart, veins are going towards the heart, and capillaries are in the middle, with many versions called arterioles and venules sort of branching away or branching towards them in the middle of all that. Honestly, you probably won't get a question about arteries or venules. They probably won't ask you about those, but they'll want you to know what an artery is. It's a blood vessel traveling away from the heart. They'll want you to know what a vein is. That's a blood vessel traveling towards the heart. And they'll want you to know what a capillary is, which is sort of in the middle, acting as the exchange site. Questions on blood vessels, guys? Feeling pretty good about that?
So when a red blood cell goes through a capillary, does that also cause blood clots when it gets stuck?
It can, but blood clots are actually like way bigger than capillaries. Weirdly enough, you'll actually see less clotting in capillaries when they're very small. You'll actually see more clotting in like veins or like arteries. But yes, you will end up with blood clotting. Like if it happens in like the leg, for instance, happens more commonly in the legs, considering that, like, you know, gravity, right? So it just has a hard time traveling back. One special thing, I didn't talk about it today, but one of the special things about veins, think about how high the pressure is when your heart squeezes, right? Pressure is really high, and then it gets lower and lower and lower as it gets further from the heart. There's a really good chart that kind of represents this, actually. Yeah. So this is actually what blood pressure looks like in the body. As it's like leaving the heart directly, it's really high. And then the further it gets away from the heart, the lower it gets. This chart's actually a little inaccurate. What it'll actually do is it kind of, I mean, it's only a little, what'll happen is there's a little spike in pressure at the very end as it's like kind of coming back towards the heart. So because the pressure's so low in veins, veins actually have special little valves in them. You'll look at an artery and you'll notice that the walls of an artery are really thick, and you'll notice that the walls of a vein are really thin. See the difference there? Picture. So that's much thicker than that. But you'll also see there's a little valve in your veins, and that valve looks like this. You can see that right here, this little valve. And what that does is if I pump blood through that valve, it kind of comes up and then the valve closes so it can't backflow. And then the next pump comes in and so it pushes it further and then it can't backflow. So you can think of it as like it goes here and then it gets stuck and then it goes here and it gets stuck. So if that valve gets stretched out, because maybe there's too much pressure, what'll happen is you'll end up with like what's called a varicose vein, which is where it'll actually stretch out all the tubes. Actually, I just saw a great picture. Where'd it go? There it is. So varicose vein, you can see here, is where all that's kind of, the valves got pulled apart. So now blood can backflow. And so it can really kind of stretch it out. And you can actually see it out, like see that like externally in the skin. I mean, look at that, that's intense, right? So that's what a varicose vein actually looks like. So if that happens in a varicose vein and blood is pooling, blood can start to clot. And with people who have varicose veins, we got to be very cautious of things like foam rolling and stuff. Because if we do have like a blood clot in the legs and we dislodge it, and then eventually it somehow starts traveling back towards the heart, it can clog the heart, and that's how you end up with a heart attack. And the same thing is true in arteries. It's way more dangerous in arteries though. If you get a blood clot in an artery, remember, arteries are traveling away from the heart so that they can deliver oxygen, right? If you get a blood clot in like your carotid artery, for instance, traveling up to your brain, that's how we end up with like a stroke, because now blood can't get to the brain. So yes and no. It's less common in capillaries, because there's so much like the pressure actually kind of builds up and it breaks it up, and so there's less clotting that happens here. But we will sometimes see blood clots form in like arteries and in veins and stuff. This is actually a picture of it, but it's really small. But you can see a blood clot forming there in this little vein. And yeah, that can block oxygen. Does that make sense? Did that answer your question?
Yeah, thank you.
Yeah, no problem. And then just so you guys know what a bruise is, bruising, which can also kind of be caused by clots sometimes. Actually, you know what, Eric? Yeah, if a blood clot does form near capillaries, the capillaries can burst because they're so small. They're so tiny. If there gets too much pressure, capillaries can basically break. Or if you get smacked, you know, you run into a wall or something, that can also cause the capillaries to basically break. That's what happens. I mean, if I punch myself in the arm really hard right now, I'll end up with like a bruise, right? And that's me breaking all the capillaries in my arm. So blood starts leaking under the skin and then you see it. And that's what a bruise is. Eventually your immune system comes along and, you know, fixes that. And it's not that big a deal, but yeah, that's basically blood pooling under the skin. All right, let's do the easy part. So let's go ahead and do the lungs here real quick. So your respiratory system, which works with your cardiovascular system, if we actually give it a job, its primary role is to ensure that you have proper cellular functioning. It keeps your cells alive, which sounds kind of weird. You know, I don't think of my lungs when I think about keeping my cells alive, but I mean, my cells need to breathe just like I do, right? Oxygen goes into them, they produce energy, and then they spit out CO2, which is why I bring in oxygen and then spit out CO2, you know? So it really is responsible for keeping my cells alive because this is the system by how I get oxygen from the atmosphere here into my bloodstream. So what's kind of weird about this is you got to think about the fact that, like, technically the air inside of your lungs isn't really in your body. Like, I know it's in your body, like it's in the tube, you know, in the chambers that are, but like when I say in the body, what I actually mean is I mean in your bloodstream. You're technically a human donut. You know, we use this analogy all the time when we're talking about the digestive system. You know, when you put food into your stomach, that food's not really in your body yet. It's sitting in a chamber of outside that happens to be running through the middle of you. You know, like you wouldn't consider, like if I put my finger in the middle of a donut hole, right? My finger's not in the donut. It's in the hole that runs through the middle of the donut, right? That's kind of what your digestive system is, you know? This is still part of the outside, you know, look, the same color. The same thing is true of your respiratory system. You're bringing oxygen into this little hole right here. Then what it's doing is oxygen molecules are so small that they diffuse through the wall of the donut, through the wall of you, into your actual bloodstream. Now it's in your body. And now I want a donut. So your respiratory system is going to work very intimately with your cardiovascular system. By the way, not every animal does this. This is how our lungs work. Bugs, they actually just passively bring oxygen straight up through their skin, or through their exoskeleton, I should say, which is why bugs are not as big as we are, thank God. But this has actually allowed us to kind of grow really large. Mammals have this arrangement, and it's one of the reasons why we were able to grow and survive in the atmosphere that we happen to live in. Dinosaurs, there was a lot more oxygen back in the day, you know, which is why they were able to be so freaking big. You know, it was a much more oxygen-rich atmosphere back, you know, 65 million years ago. So we're not as big as dinosaurs, but we're also much larger than bugs, which is great. And it's because of our lungs, right? So this empty tube travels down and then it branches smaller and smaller and smaller and smaller and smaller, right? Until eventually it ends up with these little tiny sacs here. These are called your alveoli. And those sacs are covered in blood vessels. And they're so small that oxygen is actually able to pass through the walls, kind of like a filter, into our bloodstream. Now, what's fun is that most of the atmosphere we live in, most of the air that we breathe is not oxygen. Most of the air that we breathe, 78% of it, nearly 80% of the atmosphere that we breathe is actually nitrogen. Nitrogen gas, not oxygen. Only about 20% of the atmosphere is oxygen. So what happens to the rest of that gas? Like when we breathe in, 80% of what we just breathed in is not air, or is not oxygen. So that's why we have this kind of filtration system. We have these little itty bitty tiny tubes that are preventing nitrogen from entering our bloodstream and only allowing oxygen. Oxygen's small enough that it's able to fit through the walls. So that's how this works, right? We have the two systems in our respiratory system. It's going to be divided into two categories. Our respiratory pump, which is the framework that drives all this gas into our lungs. That's divided into two phases: inspiration, which is inhaling, and expiration, which is exhaling. And then there's some bones and some hard tissue and some muscle there that's actually allowing that pumping to happen. You know, the bones like your sternum and your ribs and your vertebrae, that's heavy enough to kind of push down on your lungs and drive air back out passively. And then we got all the muscles that work actively to contract against breathing, or I'm sorry, against pressure, right? So when I breathe and I contract my diaphragm down like this, that creates an area of low pressure, which opens up my lungs. So breathing in is the active part of breathing. Breathing out is the passive part of breathing, right? So inhalation is driving gas into my lungs, and exhalation is driving air out of my lungs. That's me relaxing. Now, obviously, you can exhale forcefully. You might be thinking like, well, what about this? Right? Yeah, that becomes very active. But you're using extra secondary muscles to make that happen. Breathing in is passive, breathing out, breathing in is active, breathing out is passive. Unless you are forcefully exhaling, in which case you got to recruit some extra muscles to make that happen. So that's the respiratory pump. That creates that gets the gas into the lungs. And the passageways are where the magic of oxygen diffusion takes place, right? Respiratory passageways are the passageways that allows air to get exposed to your bloodstream. So you've got the conduction passageways, which is your trachea, this little tube right here, and then your bronchi, which are these big tubes that go into your lungs. Let's go ahead and pull up a different picture of that. So bronchi are these little tubes right here. These are the primary ones. And then they break down into what we call bronchioles, little tiny itty bitty branches from the bronchi. So just kind of like our blood vessels, right? We had like veins, and then they became venules. We had arteries that became arterioles. Well, we've got bronchi, which become bronchioles, little tiny ones. And then you've got your respiratory passageways, which are these little alveoli and these little alveoli sacs, right? So that every bronchiole will eventually end in this little popcorn sac. And oxygen's traveling into those little sacs. And the walls of those sacs are so freaking small that oxygen is literally able to pass through the walls of your body straight into your bloodstream. That's how thin, that's how small these are. Which, by the way, is one more reason why it's so important to not smoke, because we do not want to cover and break those little tiny itty bitty thin little walls, right? So there we go. That's actually a really great picture. So there's the bronchi. They get smaller and smaller and smaller until eventually they end in what we call alveoli, okay? So they look like this. There's these little popcorn sacs, right? Let's cut one open. They look like that. right? They're hollow little chambers covered on the outside with blood vessels. By the way, these blood vessels, that's the inside of your body, right? This little webbing covering the outside. That's the inside part of you. This chamber here is still technically part of outside. It's just a part of outside that happens to be running through the middle of your body, right? So we're all donuts, you know? You ever watch Gordon Ramsay? He always calls people a donut when he's mad at them. He's like, you freaking donut, right? He's not wrong. It's just not an insult like he thinks it is. By the way, this is what this all looks like. This is actually what your lungs look like inside. So that's freaking cool. So there's the body's exhibit. Look at all those little branches. Seems kind of weird, by the way. Like, why do we have this arrangement? Why not just one big central chamber? Well, think of it this way. This is able to increase the amount of surface area, which allows you to bring in way, way, way more oxygen. We just got done talking about surface area at the end of the mod in our last course when we were talking about reasons not to smoke. But think about if you had to paint the outside of a house. How many buckets of paint would that take? That's the surface area of the outside of the house, right? Well, now imagine if you had to paint all the walls on the inside of the house. How much paint would that take? Now imagine if it's just a big empty house, it's one big room. It's more like a barn, right? Man, it's gonna take what, 3 buckets of paint? I don't know. I know nothing about paint. But like, it'll take however much paint to just paint the inside chamber. But now, what if you put more walls in there? What if you, look kind of like my chart that I drew earlier, right? So now you got a house with 4 rooms in it. Well, now you not only have to paint all of this, you also have to paint this and this and that and that. That's going to take more paint. There's more surface area. Now, what if there were 8 rooms? What if there were 16 rooms? What if there were 32 rooms, right? More and more and more and more paint because there's more and more and more walls. So by having these little branches break down tinier and tinier and tinier, there is way, way, way more surface area for blood to surround, which means there's more oxygen able to get into more blood vessels. Again, this arrangement is what allowed us to bring in more oxygen, over the centuries and become the dominant species on this planet. This increased oxygen delivery allowed our brains to get more, oxygen to them, which allowed them to grow larger and more complicated. And this is one of the things that has made us the dominant species on this planet. It's also part of why we are the fastest animals on the planet if you give us enough time. We're able to use this arrangement super consistently over very long distances if you give us enough time. That is the anatomy portion of the lungs. Any questions on that, guys? Cool. All right, let's take a look at, let's put the functions together. Let's wrap it up by looking at how your respiratory system and your cardiovascular system are both going to work together in sync. So we got to talk a little bit about oxygen consumption here. Now, oxygen consumption might sound like air into the lungs, air coming out, right? What I actually mean when I say oxygen consumption, I mean how much of your cells are actually eating all the oxygen that you brought in. Because here's what's kind of weird. We think of like, and this is a good way to think about it, but like when you think of breathing, right? Air goes into your lungs, gets into your blood, your tissues use it up, they put in CO2, you exhale CO2. So if I'm being very simplistic, it sounds like air goes in, CO2 comes out, 1 to 1. But it's not a 1-to-1 ratio. In fact, you actually only consume about 70% of the air you breathe in when you are at rest. When you're completely at rest, so like honestly, probably right about now, you're consuming 70, maybe 71, 72% of the oxygen molecules that you're bringing in. The rest of them aren't really getting used. But if you start exercising, you'll start to need more of that oxygen. And you'll increase your breathing rates. You'll bring in more of amount of oxygen. So you're increasing the percentage of consumption and the volume of consumption simultaneously. You're increasing both those things, which that's a lot, right? That's a big increase. So you consume about 70% when you're at rest. And there is a moment where you are consuming 100% of the oxygen. And that moment is called your lactate threshold. We'll talk more about that in later classes. We're not going to talk about it today. But it's where, all right, I'm bringing in 100 units of oxygen. I need 105 units of oxygen in order to keep going. It's like you need more oxygen than you can breathe in. So what starts to happen is that leftover energy that you started producing, well, it just becomes lactic acid, and it's just sitting there, and it starts building up and building up and building up. And that's how you start to feel tired, right? Your legs start to feel heavy as you're running up a hill, right? You've hit your lactate threshold. You can't bring in any more air because your lungs can only bring in so much, and you can't consume any more oxygen because you only have so much mitochondria. You only have so much stuff in your body in order to do it. So eventually you got to slow down. That's why we are not unlimited in our capacity to sprint. You can only run so fast and you can only run so far. And eventually you're like, whew, I just need a minute, right? So you stop moving, which now your cells are able to kind of catch up, and your breath goes down, your heart rate slows down, right, in response. So that's your anaerobic threshold or your lactate threshold, right? So at rest, your oxygen consumption is about 3.5 milliliters of oxygen per kilogram of your body weight. We call that a MET, by the way. It's a metabolic equivalent. Don't worry about knowing this formula. You're not going to get tested on this. They might ask you what a MET is in Sochi homework. Like I've seen that question in our homework before, but they don't ask you on your test. But it's about 3.5 milliliters per kilogram of body weight. If you weigh 100 kilograms, then you're going to consume 350. You're going to consume 350 milliliters of oxygen per minute if you're sleeping, when you're at rest. Now, why is this important? Well, if you are, I think it's really motivating actually to look up what your METs are. So METs are kind of cool because you can actually look at your activities and determine how many METs they're actually burning. So for instance, like if you're playing volleyball, you're burning about 3 METs worth of energy, which means you're consuming about 3 times as much oxygen as you would be if you were at rest. That's very casual volleyball, by the way, because I've seen volleyball players and they get super out of breath. Golf is about 4.5. So we're talking really casual, standing around, goofing around with friends. Golf is about 4.5 METs. So walking around is going to consume about 4.5 times as much oxygen. Dancing is about 4.8. Backpacking is about 7. Basketball is about 8. And soccer, that's really competitive, is 10. So what's kind of fun is when you get on a treadmill and you cycle through all the options and it says how many METs you're burning sometimes. And you're like, what the heck is a MET? Well, it's like, hey, you're consuming about 3.5 times, 4.5 times, 5 times, 6 times, whatever the number happens to be, as much oxygen as you would be if you were at home sitting on the couch right now. That's how I like to use it. So I'll sometimes use it as a motivating tool for my clients. And it is important if we start tying that to nutrition. We can actually use METs to figure out how much food we're burning through. So if you're a long distance runner or a long distance cyclist, if you're in the Tour de France, METs can be kind of a handy tool to make sure that you're not burning through too much energy too quickly, or that you're not fueling yourself during a run. But honestly, guys, in a regular gym setting, METs are probably not your best tool. They don't really come up that often. A better tool to look at this is what is called your VO2 max. So VO2 is the volume of oxygen consumed, and your VO2 max is the maximal oxygen that you are capable of consuming. So go back to Eric and I earlier in our race, right? Probably the reason why my heart rate had to be so much faster than his is because he is capable of consuming oxygen more efficiently than I am. Out of the two of us, whoever is capable of consuming more oxygen, it means that their muscles have more mitochondria, which means they can put out more energy, and they're better at consuming the oxygen that they bring in. So we actually want to be able to consume more oxygen because that tells us that we're in better shape. If we both build muscle and I build muscle that has more mitochondria than you, I can consume more oxygen than you can. So now, as long as I have a cardiovascular system that can support bringing in that oxygen, I'll be able to eat it more, right? You can think of it as like horsepower, 2 cars, whichever one, a car with a higher horsepower is going to burn through fuel faster, which to me, a casual car driver, I actually don't want. I would rather have a more efficient car that burns less energy. But if I were like what do they call car people? Something heads. Greasers. Yeah, that'll work. Not the one I was looking for, but something heads. But yeah, greaser. Yeah, if I'm like into it, no, I want a car that's gonna like eat fuel and turn that into speed. You know what I mean? And that's kind of what we want in our body. We actually want to be able to consume oxygen very efficiently. So we're trying to increase our VO2 max, and we can do that through exercise. This is generally accepted as the best means for gauging cardiorespiratory fitness. So we have a bunch of formulas that we're going to use. And I'm going to teach you guys how to test someone's VO2 max later on in this class. We're going to use what's called the Rockport walk test. And that's where you make your client walk a mile and you measure their heart rate at the end of that mile and you do some big fancy math. We're going to use a calculator. And it tells you what their VO2 max is. The higher their VO2 max, the better in shape they are, at least in terms of cardiovascular exercise. Now, obviously, sometimes there's also dysfunctional breathing patterns. This is another thing related to our fitness assessments, but alterations in those breathing patterns will mean that you're not as good at bringing in oxygen because maybe you're breathing like this, right? I'm doing all this like extra muscle stuff. Again, I should be using my diaphragm, but if I'm not good at using my diaphragm, my body will find new muscles to get the job done. Just like if I can't squat properly, my body will find new muscles to get the job done. It's not good, puts more stress than it's supposed to on the body, but hey, I need to breathe, right? So alterations in breathing patterns lead to inefficiencies in your energy production because you are not able to breathe properly. So we'll see these really shallow breathing patterns that rely on secondary respiratory muscles. Primarily, for those of you who have been through our kinesiology class, the sternocleidomastoid, that's that muscle right here in the neck, the levator scapula, the muscle in the back of the neck, the scalenes, the muscles here on the side underneath the other one, which is our upper trapezius. Every one of those muscles becomes very overactive in a client who breathes like this. Little tiny shallow breathing patterns. By the way, that's how we breathe when we're stressed out. Any of you guys who have ever had like a panic attack or something like that, oftentimes that is where you're using those secondary respiratory muscles. And if you are having a panic attack, it will feel very uncomfortable. But one thing that you can do to get control again is to try to focus on breathing into your lower abdomen. Instead, try to breathe casually, slowly, and into your diaphragm, and it will help. And it will not feel like it's helping, by the way. It will make you probably a little more freaked out. But when we get stressed, we do shallow breathing patterns. And those shallow breathing patterns often lead to us, what happens is we actually vent too much CO2. And that's what's so bad about it. So here's the other thing that's bad about that and why stressful jobs are so bad for us. This alters our posture. Every one of these muscles I just talked about, your sternocleidomastoid, it's not really supposed to help breathe. It's supposed to help breathe in really stressful situations. But it is also a posture muscle responsible for this, which is not good for our spine, right? The levator scapula helps breathe in very stressful situations, but it is also responsible for this, right? The upper trapezius, it's responsible for this. The scalenes, it's responsible for this. So all of those muscles that are helping us breathe are also posture muscles. So when you use them too much, what happens? It screws up our posture. And we end up with what we call upper crust syndrome. Posture that looks like that, which is only going to further make the breathing worse, because then we're going to get used to using those breathing muscles instead of, like I said earlier, the diaphragm, which honestly, just the diaphragm is the main one. Little scalene or little intercostals as well, but diaphragm. This can lead to headaches, like tension headaches in the back of the head, lightheadedness, dizziness, all kinds of bad things. So we're trying to avoid it. We're trying to stay in shape, learn how to breathe properly, train our cardiorespiratory system, and we're trying to make sure that we are mobile in our upper body and move the way we're supposed to. So summarizing everything up, your respiratory system, it's going to gather oxygen from the environment. That's going to travel in through your mouth into your trachea. That's your respiratory passageway. The pump that's responsible for that is your diaphragm. It's going to create an area of low pressure so that that air travels down. Then it's going to split into your bronchi, into little bronchioles, until eventually it ends in the little tiny alveoli. Those alveoli are going to be covered in blood vessels, namely capillaries, the little tiny ones, right? Those capillaries are going to gather oxygen, which will travel it back to the heart. And now your heart is going to pump that oxygen throughout the body. It'll go into the left atrium, where it'll get gathered from the lungs into the left ventricle, get pumped to the body. It'll deliver the oxygen. It'll pick up CO2 from the tissue since it's done with it. And then that CO2-ridden blood cell is going to travel to the right atrium, to the right ventricle, back to the lungs so that the process can repeat. It'll drop off its CO2, pick up oxygen, right atrium, left atrium, left ventricle, body, right atrium, right ventricle, lungs, rinse and repeat forever and ever and ever and ever. Well, forever for us. So that is your cardiorespiratory system. A lot of anatomy today. It gets easier starting tomorrow, by the way. Yep, I know. It was a lot of labeling today, but hopefully that, I promise this will make a lot of sense when we start looking at our fitness assessments. When I put someone on the treadmill and I make them walk a mile and we see their heart rate is this versus somebody else whose heart rate is this, we are going to know it's like, oh, that's all the reason why this means you're in better shape. So we'll explain it to our clients, and then that will translate to more effective workouts. And, a lot of people hate cardio. So hopefully we'll be able to explain to them in a way that makes them go, okay, makes sense. I'll do my cardio, but that is about all I got for you today, guys. Any questions? Alrighty.